Today we're going to be looking at the states of matter for physical science. As you've already learned from many years ago, there are three main states of matter that we focus on. That's solid, liquid, and gas. The fourth state of matter is plasma, but we won't really be looking into that too much in this presentation. If we take a look at the first phase, solid, you're already familiar with quite a bit that has to do with it. For example, we know that solids have a particular shape, no matter what. Take, for example, a chair. If you have a chair and you knock it down on the ground, it's still going to keep its shape. We also know that solids take up a certain specific volume. Regardless if it's on the floor or up on a shelf, it's still going to have a set volume to it. And compared to a gas, we know that solids have high density, and that's because their particles are closely packed together. Something you may not be familiar with is that all objects and all matter still have some form of kinetic energy, and that's where this picture comes into play. The idea is that the close particles vibrate in place, so they're not rolling around and moving per se like a liquid would, but they still have energy and vibrate. When we take a look at liquid, we do know that liquid, like a solid, does have a definite volume. For example, a gallon of milk. We know that milk is a liquid, and regardless of if it's in the gallon, bottle, or jug, or poured on the floor, it's still the same volume of a gallon. So regardless of that, it holds its volume. As for shape, though, we know that liquids take the shape of their container. So in this example, the liquid is in a beaker. Therefore, the liquid takes the shape of a beaker. As we stated earlier, if we spilled milk on the ground, it would no longer have the shape of its container. It would be spread out across the entire floor and take the shape of the floor. Now, compared to a gas, liquids do have high density, meaning that their particles are close together. Most of the time, liquids' particles are slightly further apart than solids, but not always. So that's why we compare both solid and liquid to the gas, stating that they definitely have higher density and are tightly and more closely packed than the gases. If we talked about the solids earlier, they vibrate in place. The same thing is true for liquids. Their particles do vibrate in place, but as you know, liquids can flow as well. So because of that, they are free to move past each other. So if you want to look at liquids on a microscopic level, think of them as little tiny marbles that are vibrating, but when you pour, they roll over each other and out of their container. The final state of matter that we'll discuss is gas. And as we know, gas does not hold any particular shape. In fact, it will fill up any container that it's in. And because of that, it has no definite volume and just takes the volume of its container as well. You've experienced this before if anyone in the classrooms ever sprayed cologne or perfume. The perfume or cologne eventually makes its way and it's sent to the other side of the room. That has to do with the idea that the gases spread apart. The reason that they spread apart and go across the room is actually because of their constant random motion. Gas particles bounce off each other consistently and create what's called diffusion, which means that the gas actually spreads out throughout the room because of the random constant bumping around. As we stated earlier, we know that gases have a very low density compared to solid and liquids, and that's a good thing because we live in a giant gas, don't we? So the fact that we can move through the air shows that gas actually does have quite a low density associated with it. Now, switching from one phase to another, we're familiar with that with water already. If we look at this, and this is a solid, we look at this part, and this represents liquid, and this portion of the graph represents a gas. We see that as you go from solid to liquid to gas, there is an increase in temperature, or energy, we like to say. So as the temperature goes up, so does the energy. So if we go from the phase change of liquid water to ice or frozen water, we know that that is called freezing. If we do vice versa and go from solid to liquid, we know that is called melting. Also, if we go from liquid and turn it into a gas and increase the energy, it is considered boiling. And the opposite, going from a gas to a liquid, is considered condensing. You've seen all these phenomenons in everyday life just with water, but don't forget that this happens with all elements potentially. Just at room temperature and regular life temperature on Earth, it doesn't happen in all three phases to many other elements or compounds besides water. Here's another visual of what we just discussed. Going from solid to liquid is melting, and going from liquid to gas is boiling. Vice versa, going from gas to liquid is condensing, and from liquid to solid is freezing. What if, though, we switch and go from solid over here all the way over to vapor in one step? We call that sublimation. If we go vice versa and go from water vapor in one step all the way to solid ice, we call that deposition. So these are vocab terms you're expected to know, and honestly, you probably know majority of them already. The important thing to know about these phase changes is that they're either going to take in heat, which we call endothermic process, or they're going to give off heat, which is called exothermic process. If we look at that phase change diagram down here like we were earlier, if you are moving from a solid to liquid or a liquid to a gas, you have to put in energy. Therefore, if you're adding energy to the system, it would be considered an endothermic process. If, however, you wanted to cool something off, so go from a vapor to a liquid or a liquid to a solid, because you have to give off energy to cool it down, that process would be considered exothermic. So if you look over here, if we're ever moving uphill in the actual phase change diagram, it's going to be endothermic because it needs energy. If you're ever moving downhill, it's going to be exothermic because you have to give off energy in order for it to be at a lower state. Again, here's the same picture we looked at earlier. Either melting or boiling is endothermic. And again, the reason is you have to put in energy in order to melt it or boil it. The opposite happens then if we're condensing from water vapor to water or going from water to ice. It's exothermic, meaning you have to give off heat in order for it to get lower energy and go to a lower state or phase. We've discussed the three states of matter. Don't forget there is a fourth, plasma, that we didn't discuss today. But also we looked into phase changes and how energy is associated with that. If we have to put in energy and the system takes in energy, that's endothermic, and we heat up the system. If we lose energy, we're giving it off, that's exothermic. And that makes sense because we have to cool objects down in order to go from water vapor to water, or should I say gas to liquid. Something to think about. Thanks for listening.